Hello and welcome back to Bedside Murmurs, a podcast where we chat with doctors about the careers, pathways in medicine, clinical tips, and much more. If you have any questions or have any ideas for guests you would like to see on the show, you can send us an email at podcast@medsoc.org.au or direct message us on Instagram at Bedside Murmurs. I'm Sean.
And I'm Emily, and we will be your hosts. Today we have the pleasure of speaking with Professor David Thomas. Professor Thomas is a distinguished figure in oncology who has led groundbreaking sarcoma research and pioneered precision oncology care in New South Wales and Australia. Professor Thomas is the founder of the not-for-profit Genomics organisation, OMICO, and the director of the Centre of Molecular Oncology at UNSW. He received the New South Wales Premier's Award for Outstanding Career Researcher of 2024. So welcome, Professor Thomas.
It's a pleasure to be here.
So you've had quite a long medical career, but let's start back at the beginning. When you were going through medical school, how did you find that, and what specialty were you thinking about pursuing in the future?
Well, it wasn't at all what I expected. So when I started at university, I was a little young. I was just hadn't got my 17th birthday by the time I started at University of Melbourne. And I did arts. I was in the arts faculty in the analogous to the building in which we're in now. And I wanted to do English literature and folk studies and psychology.
Oh, wow.
But after the first year of arts, I found myself unhappy with the idea that the things I found pleasure in would become my business. And it also felt a little isolated from the real world, whereas medicine, it seemed to me at any rate, gave access to life, and then I could read in my spare time, if you like, and think about things. So I transferred into medicine, and I must say I didn't enjoy my undergraduate medicine at all. And I'm sure things have changed, so it's much more pleasurable, but in those days we had to learn the nerves, arteries and veins and their relations and so forth, all that sort of good stuff by heart.
We still do to some extent.
Good that we do.
I'm sorry to hear that. But I suppose if you become a surgeon, those things still remain fundamentally valuable, don't they? Anyway, so I struggled along as best I could until I finished my medical degree, and then went into internship, and that's just a completely different world. I'm sure with problem-based learning you get much more exposure to patients, but it wasn't the case so much when I went through, and finally that crossing the Rubicon to looking after a person in front of you and trying to make their life a little bit better was a big step. And anyway, I muddled my way through. I really enjoyed things like oncology and palliative care. I enjoyed my time out at Caritas Christi as it was then. So I had an interest in internal medicine, and I applied, much to the skepticism of the director of physician training, that she let me into the program. That's the incredible Wilma Beswick, who's still director of physician training, and has just taken my son in as advanced trainee in medicine just this year. So at St Vincent. So hi Wilma, if you ever listen to this. So Wilma gave me a chance, and it was a light bulb moment, which happened to me in my third year, on day one of my third year as a resident. I was at Preston and Northcote Community Hospital. And day one at 5 p.m, a 74-year-old woman came in with a hemoglobin of 5 and a blood sugar of 25, bleeding from a gastric leiomyoma. And all I knew at the time was this woman was on the gurney in the emergency department. And after resuscitating her and getting her sent upstairs, I instantly went to the library, unlocked the library, the tiny library at the hospital, and started to read really quite deeply. And that was really when I got deeply interested in medicine. Why oncology? Well, it seemed to me, I was interested in psychiatry, and two of my closest friends at medical school are now psychiatrists. But I decided in the end that I was less interested in human psychopathology than in the ways in which people reacted to critical moments in their life. And oncology is, as you could easily imagine, a wonderful. I've been at the box seat on watching some of the most remarkable human drama you could possibly imagine, and at the same time you could be useful, which is a really important part of the social contract, right? You're going to be privileged to witness these events, rather than just being selfish and absorbing the learnings of people's tragedies and triumphs. you should always try to give back, and oncology allowed me to do that, and it happened. So that's how I got into oncology. So I'll pause there because you might want to get a word in edgewise.
Yeah, that sounds really amazing. I think the thing that resonated with me the most is through most of the guests that we talk on the show, it seems almost as if the specialty that they end up choosing is just somehow you're struck by the impulse to pursue it, and the time frame at which they do that is completely different for each of them. Some of them knew when they were starting out, others way into internship, others have meandered along in different parts of the hospital, and then suddenly they saw a particularly inspiring mentor, and then they were also struck by that same kind of impulse. And I love the way you described it there. You just like felt the need to go and just devour books immediately, and that's something that I think a lot of people resonate with. I think a lot of people also feel that as well in the decision to pursue medicine in the first place as well.
Yes. Well, I don't think I really understood what medicine was like, and medicine's a very curious cultural world. I think it's probably not unique. I'm sure that the law is fairly similar. It has brutal hierarchies and exhausting work for the young in particular as you make your way through, but I really didn't understand. I didn't understand what it is that I eventually found really mesmerizing about medicine. What I find mesmerizing about medicine is that brilliant combination of a human focus. I mean, you can't help but feel very fond of your patients, particularly in an area like oncology, I think, where time is so critical for many people. But it's also blended with science, and this idea that the Enlightenment paradigm that you can use a scientific view of the disease to make a difference for the patient in front of you. I remember having another light bulb moment, which was when I came back from doing my postdoc in Boston. I was in a sarcoma clinic, and I suddenly realized, this is around 2003, 2004, the very early beginnings of precision oncology. We had a few drugs that were absolutely brilliant, but the idea of finding a molecular target in a cancer and then connecting the right treatment to that target was really very compelling. And I remember having this vision where I wished I could just turn around to a cupboard, open up the cupboard, and I could pluck from any one of the drugs that have been developed and simply bring it to my patient immediately. And that got me to thinking, well, how do you design a clinical trial that enables you to do that ethically and with appropriate informed consent? Because you can't just wing it in this area. You have to actually be generating evidence that allows you to know whether you're on the mark or not. That's the principle of science. But that idea that we're on the cusp of a world which had so many possibilities, and there were people directly in front of you, in the room with you, that you could potentially help. That's an incredible time to be working in medicine, I think. So I've had a very privileged career.
Wow, just as a side note, that's so smart and also so med to go like, this is something that I would like to see. How can I design a clinical trial to best test the hypothesis?
Right, well.
It's the medicine version of seed funding in venture capital.
Exactly. Well, I mean, everything is, intelligence is a really important thing. The whole idea of science and the Enlightenment is, and the reason why we now live to be 83 rather than dying at 38, which is used to be 3-4 centuries ago, has been because by taking a scientific view of the world, you can actually more accurately predict outcomes. You can say, this is likely to happen next, and since we know that's likely to happen, we should intervene to stop it from happening. And that can get right down to the concepts of molecules and atoms and structural chemistry and artificial intelligence and AlphaFold and all the rest of it that we have today. But the principle of using science to manage patients in real time, I mean, it basically allows you to go from reading textbooks, which always run out at some point for a given person in front of you, and when you have no longer the recipe runs out, the lines stop, there's an ellipsis and there's nothing, then you can turn to science and say, well, what makes sense to do here? And to use as much of your knowledge as possible to make the best informed guess you can, and then, most importantly, to record what happens next. And that's been wonderful. Actually, I couldn't have imagined when I was an art student ever going into science. So going into science has been a very unnatural act for me, but it's turned out to be a really wonderful mix. The humanities, the humanities and the science.
It sounds like science has been at the forefront of your career. As a doctor, but also working in science, something that a lot of people are terming clinician scientist, what does that role involve for you on an everyday basis?
Well, it means exactly what I've just been talking about. It means as a clinician, you use the science in your clinical work, and you let your clinical perspective inform your science. I mean, think back to the 19th century when, people like Laennec listened through a tube to the chest for the first time and heard lub-dub. This was using technology to get this sudden insight into something that was going on inside someone's chest. And that's the beginning, of course. Then you hear the mitral valve prolapse and all the rest of it that you can hear if you're listening to a heart's function. But the idea that you today have in a cancer patient, they come forward to you and you have these incredible tools like genomics to be able to apply to their problem, knowing that the outcome of the genomics can lead to decisions that will go directly back to the patient. It's almost like going back to the 19th century and using the principles of science to solve problems that are immediate in front of you today. As a clinician scientist, that's the best of it all. You're not reading from a cookbook, which there's no doubt that doing things regularly and properly is not only clinically good, but it's also legally required. So it's in a very constrained environment, though, there is definitely a place for smart, outcome-driven improvisation, which is, I think, what clinical science is about.
And what are your primary research interests as a clinician scientist?
Well, it's genomics and cancer. And, okay, so why? So cancer is fundamentally a genetic disease. You think about the 3 billion sites in the human genome, 6 billion nucleotides, roughly, in every cell, starting from one cell and finishing with the 70 trillion cells that make up the average human. The copying of that code is like copying out perfectly 56 entire sets of the old Encyclopedia Britannica, which you two are too young to actually ever imagine. Like that used to be about 26 books in one volume set, and there are 56 of those, equals the number of letters in the human genome.
Oh my.
And we know that genetics is important because really since the 19th century we've observed families where there's too much cancer. That's proven that the genetic components can drive risk of cancer, as it does for many diseases. What became clearer in the 1950s, 60s and 70s was that same genetic material in the tumor lump was also important in somatic evolution of those cells to become cancer. What turned a good cell to make it bad is not the genes that get mutated that you inherit, but overwhelmingly the mutations that cell has undergone since that time to corrupt the code. Now, knowing that that's the case allowed us to identify the first human oncogene, which I think was Harvey-RAS. The RAS gene, which was identified from a cell line by a guy called Cliff Tabin in 1982 by isolating the fragment of the RAS proto-oncogene, isolated from a bladder cancer cell line that would result in transformation of cells in culture. And what he did was it was really clever. I mean, think about the technology and the way it's advanced over the past 50 years or so. What he did was he took the full-length coding sequence for Harvey-RAS, which was mutant and could transform when introduced in cells. Then he chopped it in half and cloned it to a wild-type sequence of Harvey-RAS, and it lost the function. So they knew that the bit they chopped out contained the mutation that caused it, and they progressively chopped it up until they isolated the specific codon in the RAS oncogene, which was responsible from a normal gene function to something that would cause in vitro the equivalent of tumorigenesis. And that was the first oncogene that was identified to be mutated in a human cancer. And now we can sequence the whole human genome in the space of 48 hours, get every single one of those nucleotides, at least in principle, accurately mapped. And we can get a catalogue for each individual patient of the mutations that are present in their tumour. And in parallel, rational drug development has now developed drugs to hit specific ones, an increasing number of those mutations. In our program, for example, today, about 70% of the people that come in who've run out of treatment options, we will find a target by sequencing that tells us that there is a drug that could be used to hit that target. And in about half that number, or a little over, say, 37% is about the number that we've got, 37% of patients who come into our program will have a target identified that would otherwise be invisible, and that drug target has phase 2 or better evidence for extending survival, and only visible through the lens of genomics. So, I mean, that's just one example of genomics in cancer care. It's the one that's most urgent because people's lives are on the line usually in these they don't have any time left. They need treatment options, and they may have a median survival of a year. That's typically the scenario that we deal with. But there's also genomics in that heritable sense. I reckon probably 1 in 10 of the cancer patients that we see probably has a genetic cause. And particularly if they get cancer at a young age, I'm sure you guys know amongst your peers that there are, via your network, somebody who's had cancer at a young age. It's thankfully not common, but it does happen. And in those cases, it's more likely that there's going to be a genetic cause. So if we could identify that as part of routine medicine, looking after the patient, that we identify the genetic cause, then after we've fixed their cancer, which occurs in about 85% of early onset cancers, then we can turn our minds to the question of how do we keep that patient free of the next cancer they might develop. That's a model that's been around for decades in cardiovascular disease, but it is still not standard of care. It's going to be you guys, if you go into oncology over the next 10 or 15 years, that will see that model changing so that every person who gets a cancer young has a whole genome sequence to identify why it happened and then to maximize the exploitation of that knowledge to improve your wellness span after the hurly-burly's done for that cancer. So I think I can see the future, and it's at least over the next 5, 10, 15 years, I won't be around to see it fully mature. But because of the advances in genomics over the past 10 or 15 years, because of advances in cell biology and in drug development, because of advances in things like artificial intelligence through AlphaFold, the Nobel Prize for chemistry was for AlphaFold. It basically bypasses what would take 5 to 10 years of structural biology and X-ray crystallography, can now be done in silico immediately. All of that basically takes the principles of precision medicine, which is a molecular view of medicine, and accelerates the rate at which can be brought into something that will help a patient today, or if not today, then tomorrow, and if not tomorrow, then in a year's time. I used to think that you'd be wary about talking about the future of science to a patient who had incurable disease, because who knows what will happen it might take 5 years before we have a breakthrough. But I don't think that's true today as it was back when I was a registrar and a resident, when we only had chemotherapy for the majority of patients. So I guess what I'm saying is my own areas of interest in oncology are driven by the fact that cancer is the leading cause of death in our society in higher income countries worldwide. It's a genetic disease. We now have tools to decode that genome in every cancer, and we have tools that allow us to use that information to improve the quality of life of those patients. And so that brings you back into full circle. As a clinician, it's absolutely brilliant.
This might sound like a contentious question, but how close do you think we are to a universal cure for cancer?
Yeah, I don't think there's ever going to be a universal cure for cancer, because there isn't any. You've got to think about the difference between normal cells and cancer cells. You think about chemotherapy, for example, where we really didn't know how these drugs work. We targeted cell division. Now, it's obvious to do 1 week of embryology, and to get from one cell to 70 trillion cells, you've got to undergo cell division. Cell division is going all the time, and therefore you could predict that chemotherapies that target cell division aren't just going to affect cancer cells. They're actually also going to affect normal cells with significant side effects. At least with precision medicine, you could identify the unique molecular fingerprint in a cancer and then bring the right drug to changes which are only present in that cancer, not in normal cells by definition. So that's one element to it all. And I think we're at the era, about 15 years old now, of rational drug development. So, for example, in 2017, there were no FDA-approved tumor-agnostic therapies, or therapies that would work in any cancer type that bore the molecular target against which the drug was designed. And now we have 9 approved therapies. By 2025, it's likely that we'll have 30 by 2030 because of the nature of progress. So we've just got into the era of developing these drugs. What we haven't yet got into is combining those drugs. The drug fluorouracil, which is used for colorectal and other cancers, you probably know it. It was probably brought into the clinic in the late 1960s, but it took 30 years of dosing, scheduling, combination therapies to optimize the use of fluorouracil. Why would we think that these new drugs we develop won't go through the same? The drugs we have today won't go through iterative dosing and scheduling discoveries which will make them even more potent than they are today. And when we combine them together, maybe we'll be able to get that antibiotic model where one antibiotic can control an infection, but two will actually eradicate it quickly and potentially without the harm that follows from sepsis. And I think those models will apply. Then there's the discovery of new strategies like immunotherapies. Harnessing the immune system has been a categorical breakthrough in the past 10 years. And I don't doubt that there will be further breakthroughs in areas of epigenetics and so forth over the next 10 years and beyond that we can't anticipate yet that will will increase our armamentarium, fill my cabinet that I wanted to reach into when I was a young oncologist. So, but I don't think it will ever be that you'll take this pill and the tumor will go away. And I also don't think that surgery will completely disappear.
Okay.
Because surgery is still critical to the cure of the majority of patients. So we're not talking about a brave new world in which nothing of the past remains. There'll be a slow integration of these new discoveries into a way that we cure cancers today. Hopefully leaving not only higher cure rates, but actually less morbidity in the longer term for survivors. Survivors of early onset cancer, for example.
With much of your work, you've also founded OMICO. Could you tell us about that and what happens there and what prompted you to found this organisation?
Yes, it's a bit transgressive, isn't it? Well, I mean, maybe that's sort of one of the lessons from research that you have to be prepared to take on new ideas. That's right. So OMICO was founded because we had set up an infrastructure within the state of New South Wales which is offering genomic profiling for patients who've got incurable cancer. And we had eminent individuals flying from Perth to get onto our program here in New South Wales because it was clearly at the cutting edge of options for patients. Well-educated people travelled to come onto the program. And when we realised that and we thought about, is it ethical that somebody with stage 4 cancer, metastatic disease, has to hop on a plane every month to come across to Sydney from Western Australia? Surely we can do this without having people with advanced cancer having to travel, at least to get the test. The treatments might be more complicated, but at least you can get the test done. And so we put forward a proposal to the federal government to nationalise the program we'd set up. And the federal government quite reasonably said, well, you know, we've got 8 states and territories. The hospitals, which is where you're going to do your work, are all funded to the states and territories. Show us how you'll be able to deliver this through the hospital networks in every state and territory. And so we contemplated the idea of having to negotiate with 8 state and territory governments to get to the starting line. And we decided that was out. So what we did was we created a company. And companies are a really interesting structure socially for joint enterprises where you collect the investments and then you use those collective investments for certain goods. And we set up a non-profit company because our mission was to improve the quality of life of Australian cancer patients. And the members of the company, when we set it up, were cancer centres in each one of the 8 states and territories. So we started off with 8 centres and now we have 79 centres that are part of our network. Amazing. And it's just grown from there. It's also, as an experiment, taught us a lot about the parts of the system that become rate limiting. When you've got an idea that's working, how do you scale it? And how do you sort of push that idea until it becomes hopefully mainstream? And a lot of that is about freedom and engagement and collaboration and thinking about not just the health impacts but also the social, the economic impacts of what you do. And when you set up a company, you're able to fully and freely explore that in a way that a university, I think, struggles to do, in the way which governments cannot do because of their conflict of interest and probity rules, but which as a non-profit entity we were able to do with a greater degree of freedom. We were able to imagine what it was like to be a for-profit entity developing drugs, for example, and to work constructively to get the best outcomes for patients. And ultimately, we needed to do that because without the companies, you have no drugs. And with no drugs, you're not helping anybody.
No.
That's really interesting. As you were saying and speaking that, I was like also struck by just your ingenuity when you are trying to solve a problem. Like, firstly, when you thought of the cabinet solution of like, I want to find the best ways to help the patient. I want to try to design a clinical trial to try to develop this cabinet of tools that I have. And now, in order to provide healthcare across all 8 states, I'll just start a non-profit company in order to bypass the obviously strenuous exercise of applying for successful federal sponsorship, which is, I also understand, terribly difficult. That's where does that kind of inspiration come from, do you think?
Well, I guess it's based in optimism, isn't it? And confidence that the questions that you're asking are important enough to justify bold ideas, and also out of a cynical and harsh criticism of the alternatives. If you don't have to create a company to achieve your objects, then by all means save yourself the time and effort of going to do the Australian Institute of Company Directors course. The whole world, running a company. I was chief executive officer of the company for 5 years, and it's a completely different world, which I've learned enormously from, and from my colleagues who come from that world. So if you don't have to do it, you shouldn't do it. But if you have to do it, then you either you're paralyzed and hang back, vacillating, or you say, this is an exciting thing to do. It's novel. I've thought through it carefully. I can't see the downside. I've discussed it with people, and they don't think it's an insane idea either. Let's have a go and see what happens. And it's been overwhelmingly effective as a vehicle for allowing engagement in the scientific enterprise, in the clinical scientific enterprise, of people from walks of life that would otherwise not be able to get into the environments in which we conduct clinical science. It's allowed business people who think about drug development. It's allowed people who think about real-world data. It's allowed people who work in the banking industry and want to give back. It gives them an opportunity to also play a really essential role in growing a program from zip to something that's worth $230 million over the past. $250 million has been focused through that vehicle into trying to make a difference for Australian cancer patients.
That's fantastic. It's really great to hear how precision medicine is being integrated so well into current care and driving the future of oncology care. So it's been such a joy to hear about that. Thinking about when you started as a medical student though, how has oncology care changed? You mentioned the future of oncology, but how has it changed since you've been in medical school?
All right, well, I'll give you a few examples. So when I was, I first became an orderly in the front of casualty at St Vincent's Hospital in 1981. I just turned 17, and I would wander around helping the nursing staff and the doctors manage the unfortunates, the people who, for whatever one reason or other, wound up in the emergency department. When I became an intern, a medical student, I would be putting in gelcos, we would cannulae, and there were no gloves. This is pre-HIV. So
wow.
That would be a different world, yeah.
Yeah, so we didn't have universal precautions, and it's hard to feel a vein, as you know, through a rubber glove, through latex. So, it was a world in which the degree of risk aversion was probably lower, and maybe the innocence and ignorance, frankly, of the consequences were lower. I would go in and auscultate regularly in my morning rounds somebody inside with active tuberculosis who was fortunately in a single room, but we didn't gown up. We didn't have, washing things at stations. It wasn't, and it just go in and do your job as a doctor. Now, all of that has obviously changed, and most certainly for the better, I would guess. But if you think about oncology, we used to admit people who had received testicular cancer, curable disease at that point with cisplatin. We'd have to admit patients to the ward to stop them vomiting for 3 days after a dose of cisplatin. Then 5-HT3 antagonists, things like ondansetron, the antiemetics, came along and they transformed that, and it became an outpatient discipline. Oncology was very much more an inpatient discipline. Today it's largely something that can be conducted outside of hospitals through outpatient departments, and even at home. And that wasn't the case. And that's leaving aside the advances of science, imaging techniques like magnetic resonance imaging. When I was a medical student, we didn't have the ability to take a section through the human body and to point out all the layers and planes of fascia and organs and bones and so forth that we can see today. That all has happened since I was a medical student, let alone genomics and genetics. Genetics, and I still see this in the textbooks today, genetics is taught as a dominant Mendelian disorder. Have you done genetics, you guys? So overwhelmingly, my guess is that you've been taught about, you have two genes and it's recessive or dominant, and you can have X-linked recessive and you have to do those Punnett squares and things. It's all a very monogenic, dominant and Mendelian, as though one gene controlled everything about a person. And I can tell you that world is completely transformed. We now know that genes don't operate as singletons. They don't just deal with rare variants that cause these rare syndromes, but in fact there are common variants that operate as battalions. They come together in an individual to produce catastrophic effects. This world that we're going into, it's like going from black and white into colour. And you guys are still probably learning, for the most part, the basics of dominant Mendelian genetics, something that's esoteric and applies in a minority of the diseases that you're interested in. For cancer, it's going to be 1 in 10 people. And it's not going to be just one gene, a rare gene. It's going to be 2 genes, which are a little bit more common, or 5 genes, or 5 variants in genes that actually are so common that you actually have 1 in 20 people who comes in with prostate cancer having these polygenic risks. And we don't have the tools properly to implement that, but we know they're going to come. So what I'm describing is not just the changes between when I was at your age, at your stage of your careers, to where I am today, but even this world shares my experience of genetics and the way we think about genetics academically. A lot of this stuff has evolved so quickly it hasn't even entered the undergraduate curriculum, which is why research is so important to you guys. And if I have one thing I would like to share is be passionate about your medicine, realize its limitations, and realize the only way to overcome those limitations is through science. So never get out of the habit of thinking in a scientific way about how you can help your patients in front of you, and you will have an absolutely wonderful time in your careers.
Well, I thought of, as you just said that, a lot of us in research here right now, 4th year, we're doing like an entire year where we follow a supervisor, we do the research, essentially. It's kind of frightening a little bit, but also kind of inspiring in a way how much we don't know in comparison to how much we do know. And I kind of had this thought as you were saying what you experienced going through medical school and as an intern. When a patient comes in the door with a fairly like ambiguous presentation, like they're vomiting or they're just generally sick, perhaps back then there was only a few things that you could do in terms of treatment, but now the more we know, the more we're able to image, the more we can see, the more like we realizing that, there's like so many different fonts of the same sickness, of the same presentation, and all of them are very unique presentations, and a lot of them we have no like prior knowledge for because these are all new discoveries. And as we open up like the floodgates of like, we're discovering polygenic diseases and different types of inheritance on cancers, it's a kind of like shining a light on how much little we actually know about how to treat them as well.
Well, in the end, you've still got a patient in front of you, and you know, a surgeon would say, forget about all that crap.
It's there, cut it out.
Exactly. And they're probably right, because when a person's in dire trouble, somebody's got to not say, give me a chance to have a think about that. Let me do some research and I'll come back to you in 5 years. You have to make decisions with people in front of you now. And that trains you into a kind of pragmatic set of creativity where you have to balance that against completely... You have to recognize, though, when you're straying off-piste. That's probably the key thing. It's perfectly legitimate to go off-piste when you have no alternatives, but you have to know where the boundary is, because you don't want to forego an effective therapy in somebody because you're improvising. So you do have to know the boundaries between what we do know and what we know is effective and where we've run out of options, and you still have to somehow act in the interest of the patient, and that's the domain in which research lies. There is one final comment I'll make about that, though. It's important not to throw the baby out with the bathwater, because one thing that science and hope. Science is reason-driven hope. It's not completely irrational. It's got a very strong evidentiary base that we can place some weight on that hope. It's not like flowers and spices or, homeopathy or things like that. Whatever the merits of those approaches are, this is something more substantial. But you need to avoid, hope is an extraordinarily combustible inflammatory site. It's like oxygen. It burns. And for somebody who is in the terminal phases of their illness, you can be pinned to the board like a butterfly by science, and a good doctor knows when to make the transition between doing everything you can and when it's time to allow people to go through the natural journey that ends our lives. And that's palliative care. And it's easy to get so absorbed in the molecular universe to forget that you're dealing with a patient and a human being. And certainly I, as a patient, I look for a doctor that I find kind and thoughtful and will communicate with me. And that's a really interesting thing. That's where a scientist is influenced by being a clinician. If that's the world that you want to operate in, that's a very privileged space.
Well, thank you so very much for joining us today, Professor Thomas. It has been such a pleasure to have you here, and it's been such an interesting discussion. Thank you so much for coming on.
It's been a pleasure. Thank you, Sean and Emily.
Amazing. Right. Good job.